Our next speaker is Dr. Bruce Mathews. Bruce is Dean and Professor of Soil Science and Agronomy at the College of Tropical Agriculture, Forestry, and Natural Resource Management here at University of Hawaii of Hilo. Bruce's research focus is nutrient cycling and soil fertility. Bruce?
Aloha. And Hawaii was actually once a rice exporter, something that's often neglected in the history when it's discussed of our islands. It immediately presented some sustainability challenges because it's one of the earliest examples of intensification. We hear a lot about agricultural intensification today to produce more out of less land. And a really prophetic paper was produced by USDA by William P. Kelly in 1914 in Rice Soils of Hawaii, where, like many cultures and peoples around the world, Hawaiians and others would use fertile alluvial soils to produce crops on, and it worked. It worked for a long time. But when they tried to produce more by adding ammoniacal fertilizers, they started to have nutrient depletion problems. And Kelly was one of the first ones to point out that potassium and phosphorus were beginning to be depleted with higher yields, the double cropping of rice rather than single crops. And when we talk about sustainability of indigenous systems, we often fail to realize that they had a success in part due to less extraction and lower yields of the native varieties and high human resource availability without the economic pressures of global trade. Next slide. When we look at making Hawaii sustainability, there's a land use challenge. When you look at how much land area is needed to feed a normal human, it takes about 1,500 meters squared of land area. But in Hawaii, we only average 300 meters squared of land area under cultivation, and much of that is not done for staple crops at all. I mean, we have some kalo, taro, we have sweet potato, but much of it is for export, for novelty crops, niche crops, superfood crops, etc. And when we talk about food security in island settings, many of you may have seen in the Civil Beat article earlier this year where there was citations about the U.S. military doing studies just prior to World War II in the 1930s about what it would take for an island to be sustainable if it was cut off. And this was later followed up by A. Duncan Brown in his book Feed and Feedback in 2003, that food security would require the island at the point it was cut off to be producing about 70% of its staple carbohydrates. At present, Hawaii imports about 85% of its food supply, 94% of its energy, and that food supply importation, according to UH Manoa CTAR economists, costs the state about $3.1 billion, leaving our state annually for food. When we go back in time and look at native Hawaiian land uses, the island of Kauai in the top left corner, there was very little use of uplands because they had a lot of fertile valleys. But then when you go to the bottom left, you see on the big island, Hawaii Island, that there was just small gulches on the Hilo Hamakua coast that were used for kalo production. Of course, there was Waipio, Waimanu, and Pololu valleys that provided for wetland taro. But as the population expanded, they had to find the sweet spots of soil fertility in areas where there was enough rainfall to grow crops, but the rains were not so intense that the soils were nutrient depleted from leaching. Next. So this is just a blow-up of the Big Island, and for both from two different sources, from Vatusic and from Noah Lincoln of CTAR. And Noah Lincoln was one of the ones that pointed out along the east coast of the Big Island, the Hilo Hamakua coast, we did have agroforestry to cope with the high rainfall soil conditions that weren't conducive to annual row cropping, and there was limited slash and burn to grow a crop of upland sweet potato and then fallow the land for long periods. So it was more of an agroforestry-based system, and NOAA is currently exploring the role of agroforestry in native Hawaiian agriculture to a great extent. Next slide. Rainfall drives a lot of our agriculture and what is growing in terms of the area's wetness. The green areas actually show the areas that are more ideal. They're particularly the darker green areas that where there's enough rain for good crop production, not excessive rain, where all the nutrients are leached out of the soils. And many of those areas were areas where the Hawaiians farm. Soil weathering is quite simple in Hawaii, that we start with the volcanic parent materials, the lavas, the a'a, pohoihoi, and volcanic ash. And as they weather, nutrients are released and accumulate to build fertility. But over time, there's nutrient depletion and accumulation of iron and aluminum oxides, and the organic matter levels decline, in part because as the soils develop more crystalline iron and aluminum oxides, less organic matter is stabilized, so there's overall fertility decline. Likewise, with the levels of bases, but calcium, magnesium, potassium, they tend to decline with high rainfall areas, or the only times you actually see low bases nutrients in low rainfall areas is that it's very old soils. There's a bar on the right side showing age of soil. And the same with pH. The pH tends to decline with high rainfall areas. The gray bars actually demark the areas where evapotranspiration is less in equilibrium with rainfall, but beyond that, to the right of the gray bars is where you expect the greatest nutrient leaching. This work was done by Oliver Chadwick of UC Santa Barbara. Next slide, please. So basically, you can look at soils. I often showed this to students when I taught, that you can have soils in moderate or low rainfall environments that are rich in nutrients but lacking water. But in areas with high rainfall, you often end up with very infertile soils, and you need the nutrient inputs. In terms of Hawaii's soil diversity, we have 10 of the 12 soil orders of soil taxonomy, and 6 of them exist on the Big Island, which is quite amazing given how geologically young the Big Island is. So on this graph kind of shows what we start out with. On this island, we start out with shallow histozols, which are organic soils on top of rock, a'a and poihoi. And then we have the volcanic ash soils, the ondazols, which form from the ashes and form minerals like allophane and ferrihydrite. The more ferrihydrite, the more the phosphorus that's tied up in the soil. And both of these soil types tend to have low bulk density compared to older soils. Eventually, soils weather into inceptizols and mollyzols particularly in moderate rainfall areas, and they are some of the most fertile soils in Hawaii, like in the central plain of Maui. And then as soils become geriatric or old or senile, they end up with a lot of iron and aluminum oxides, kaolinitic clay, and don't hold nutrients as well. But all these soils have pretty fine physical properties for the most part, particularly the ondazols. Some of the ones in high rainfall areas may be very infertile, but their fertility can be brought up. They have great physical structures. Even in many of the ultizols and oxyzols have fine physical properties. Next slide. In terms of fertility class of Hawaii soils, on the Big Island, the yellow shows the ondazols that are very ferrihydritic, leached ondazols that are not as fertile, and the blue areas on the Big Island show the soils that are more fertile, the fertile ondazols, oostans in mid-rainfall environments, and the brown areas show where a lot of these shallow histozols are. So the shallow histozols were often commonly used for crops like papaya and greenhouse operations. And then you look at the infertile ferrihydritic ondazols, like of the Hilo Hamakua coast. Today, when you look at abandoned cane fields, a lot of times you can visually see the low nitrogen availability by the yellowish tinted grass. And then the fertile ondazols of the Waimea area are very good for vegetable production. On the older islands, you have a lot of infertile ultizols and oxyzols. But the central plain of Maui is important to look at because, it was the last sugar plantation to close, and obviously it was the sugar plantation area that had the most fertile soils. Next slide. Sugarcane plantations, they often use lands that the native Hawaiians did not intensively cultivate because they could modify them with soil amendments to make them more, and fertilizers to make them more productive. They also use fertile lands like the central plain of Maui. Next slide. So a lot of times I have students come to class and they would talk about organic matter. Yeah, organic matter is important, but I can show you many soils where you have a high level of organic carbon, but they're not holding nutrients very well because the charge of organic matter is very pH dependent. If you keep the soil's pH above 5, and you can see in the bottom graph, their cation exchange capacity goes way up. In addition, liming causes a lot of the groups on the edges of clays and iron aluminum oxides to release the hydrogen so that frees up exchange sites to hold more nutrients. And over half of Hawaii's soils are acidic. Next slide, please. So one thing that's interesting to point out, as I mentioned, many of our soils have good physical properties. Back in the 1930s and 40s, the inherently fertile soils, like the mollyzols on the central plain of Maui, far out yielded the cane soils that were under the low fertility soils. But through soil amendments and fertilization, by the 1960s and 70s, the cane yields were equal or higher on the infertile soils with their fine physical properties. And so this was an important concept that actually drove a lot of Hawaii's technology export. How can we make the tropics productive by modifying the soil conditions? Next slide. And another thing that was driving it was Hawaii has very similar distributions of phosphorus and potassium fertility as many areas in the tropics, very similar to places like the Philippines and much of the Philippines and Brazil, and phosphorus and potassium were very frequent deficiencies. Next slide. So this led to what I look at as like one of the most important innovations of modern agriculture in Hawaii was the Benchmark Soils Project and the NIFTAL projects. The Benchmark Soils Project was looking in the soil management from the fertilizer and soil amendment and crop variety realm to see how we could transfer what works in Hawaii to other places in the tropics to address food security issues. And NIFTAL's project was, well, what kind of rhizobium, nitrogen-fixing legumes can be modified or adapted to tropical soils? And so basically the attempt was to achieve yields comparable to temperate agriculture on tropical soils and transfer that technology. So similar soil types, similar climates, how can we transfer that to other countries? But when you look at that today, it was also with increasingly costly non-renewable fertilizers and inputs. And this is becoming an issue like in Brazilian Cerrado, which currently produces soybean yields similar to the Midwestern US in terms of yields and production, but the inputs are becoming challenging for Brazil. So next slide, please. So when we look at green revolution, everybody talks about irrigation, nitrogen fertilizer, varieties, but it was also driven a lot by phosphorus fertilizer. And as I think Richard alluded to earlier, it's a non-renewable resource. It's not recycled very well. Russia and China currently produce 40% of it, and it's becoming an issue globally with the rising costs and how to keep tropical ag going. With this non-renewable resource. It's increasingly expensive to mine. I think Morocco produces about 70% of the raw material. So it's not something that's equitably distributed through the world. I've always found it ironic that there's so much phosphorus deficiency in sub-Saharan Africa, but very little of the phosphorus that's produced in or mined from Morocco actually ends up back in Africa. Next slide, please. Okay. So when we look at like Brazil, one of the original goals was to say that the phosphorus deficiency could be addressed by a massive input or a large input that could be amortized over time and that we wouldn't need so much. But currently 30, 40, 50 years after the initial bringing these rainforest soils into cultivation, they're still requiring high phosphorus inputs. Next slide, please. And this is driven in part by what I can look on the right is that when the soils bind phosphorus, there's diffusion of the phosphorus back into the inner part of the soil by diffusion or absorption into the soil particles, so the surfaces can resorb more phosphorus. And this can be shown simply for here in Hawaii with an ondazole, an udon, where 750 kilos have been put in over 30 years, and it still has high phosphorus absorption capacity, while a malazole with a more crystalline mineralogy has a lower phosphorus absorption. It's even decreased more by the phosphorus input. So mineralogy plays a huge role in the sustainability of phosphorus management. Next slide, please. And so does soil structure. Excessive tillage makes more surface area for tying up phosphates. Next slide. So where we're at now is how do we improve efficiency of agriculture? And like the Kalavo enterprise in Puna, they study their farmers. What farmers are making the most profit and how, and then helping share that information with other farmers to be more efficient. Many industries have shown that just by studying your farmers and finding out what the most successful farmers are doing, and then sharing that with other farmers can increase profitability of the industry by 20%. Next slide. So we have no really fertilizer security in Hawaii. We don't make any of our nitrogen fertilizer, although Richard can say we can, maybe use geothermal power to make power the Haber-Bosch process. We have no mineable sources of phosphorus, potassium, so that means we have to look at recycling eventually. Next slide. So, what can we recover from sewage? Urine diverting toilets. A lot of concerns about sewage with heavy metals, but not so much in Hawaii where we don't have a lot of industry. Is there other ways to capture nutrients from sewage? Again, phosphorus is non-renewable. Potassium is non-renewable, but phosphorus will run out way before potassium. Next slide, please. So, industry. Pacific Biodiesel. They get potassium sulfate, which can be used as a potassium fertilizer as a byproduct, but they can't do that because it's not an industrial approved process. Next slide. Yeah, energy cane, if we do make jet fuels and things out of it, same, we could precipitate phosphates out of it when we do the clarification processes. Next slide, please. So can we make biofertilizers like Kula Bio, where they use associative nitrogen fixation to make associative fixers that could supply nitrogen? And then, next slide. Nick Comerford of CTAR did a lot of work early in his career. How can we make phosphorus more available through plant exudation? I'll just say this, in root structure, I don't have a lot of time. Additives to soil to try to make nutrients more available for plants naturally is a $2 billion market and increasing, and a lot of it doesn't work that great, but there's tremendous opportunities to make nutrients more available through biological processes and changing the root structure of plants, etc., changing the microbiome. Next slide, please. Another thing you'll probably hear about during this conference is nanofertilizers. They're expensive. Gavin Gilman from Australia came in a couple years and talked about nanofertilizers to improve fertilizer use efficiency so the nutrients don't leach, they don't get bound up by the soil and act as a slow release. Next slide, please. So the whole sensor technology thing, there's tremendous opportunities there. And I've got to say, that's one area where we're beating China right now. They have the technology, but they're not using it to the extent American ag is. And I've had scientists from China tell me it's because the fertilizer is too subsidized in China, they don't look at using these technologies to become more efficient with the sensors, the drones to do field maps of fertility, etc. Next slide, please. And of course, modifying soil structure for healthier soils due to different crop rotations, making ideal pore sizes for the microbes can do their work, sequester more carbon more effectively is another important area for the future. Next slide. And so the question is, where do we go there from in Hawaii? I mean, we're in a thing now where we've lost a lot of industries. The seed industry is even declining. Aquaculture is growing a bit. That's a big question. Next. And so we have the climate change challenge. It's in the newspaper regularly about ranchers here dealing with droughts and higher temperatures, less frequent rainfall, etc. Next slide. So Pacific peoples, they adapt similar ways to deal with the stresses, unique but also similar. And all I can say is that in my time as a student in Hawaii in the 80s, I met a lot of people who came through the East-West Center. They came through the UH programs. They became leaders throughout the world. and they kind of wonder what happened to us. They said we were once the Switzerland for ag technology, and where people would gather, we were innovators, and they said we've kind of lost track, but they would welcome it again. They actually miss it. They wish we could become the gathering place of technology for people of the Pacific. Mahalo.